welcome back. Eric Taylor here. This lesson we're learning about weight and balance calculations. Let's go. The aim: to ensure the aircraft is loaded inside operating limits before flight. If you don't know this already, obviously this is a very, very important part of flying and aviation. We want to make sure that we're within limits, and we're going to do this before each and every flight. And the reason why we're going to do it manually before each and every flight is that at first it is a little confusing, but with practice and doing it before each flight, it'll become very, very intuitive, easy. You'll have a lot more confidence when you're on your check ride and the examiner asks you to perform a weight and balance in front of them. And so that's really the primary reason why I encourage my students and require them to do it before each flight. And so that's what we're going to learn. We're going to learn how to perform that weight and balance in this lesson. Here's a look at the Diamond 20 weight and balance. So we can see weight and balance for the Diamond 20. And we'll go over quickly a few of the parts to it. So here we have the CG envelope, is what we would call that. In this section we have weights of the airplane, passengers, baggage, fuel, and then from there we have the arm and moment, so we'll learn about that in this lesson. Down here we have some performance data, so takeoff and landing distance, and we're going to input that data there, and then over here on the back would be the charts we use to input that data. So this is what we're going to be talking about in this lesson. All right, a few questions to start with. How are you going to know how many people you can carry and where they should sit? So how much weight can you carry in the airplane? What's the maximum amount of fuel you can carry while remaining in limits? So there's going to be the maximum you can fit in the tanks, but then there's also going to be the maximum fuel we can have depending on how many people we have in the plane. And then what are your options? So are you going to reduce the people in the plane, reduce the fuel in the plane? You're going to have some options, and that's what we will learn. Some terminology. We'll start with the datum. So datum is an imaginary line. We could see this one here. It's at the engine firewall. So datum is an imaginary reference line that the manufacturer makes up, and in this case they put it on the firewall, and then from the datum, this reference line, that is where we'll measure the arm lengths from. So we could see here that any arm, which arm stands for a distance from a known reference point. So if the arm is ahead of the datum, it has a negative number, and then measurements taking or arms taking from the datum past it will have a positive. A few other things. We have the CG range. So when we're looking at that chart at the top of the weight and balance, there's a CG range, and then so there's a forward limit and an aft limit, and then that's just represented visually right here. The other thing we'll just take a quick look at is we have a moment of 700 pounds, and how we got that was the arm length for this station right here is 70 inches. There's 10 pounds of baggage back there, and then so 70 times 10, we get 700 would be a moment. Don't worry, we're going to talk about that real shortly. But the things that we need to learn from this are some basic terminology. Datum or reference line set by the manufacturer, arm or distance from datum, and then we have a forward limit, aft limit of our CG range. Must know information. A few things we need to know. Weight times arm equals moment. Go ahead, commit this to memory if you don't know so already. Weight times arm equals moment. And then from that equation we could get our CG, which is another word for arm, which is the sum of our moments divided by the sum of weights. So then if we go back up here to this top equation, if we want to solve for arm, then we'll need to divide the weight to get it over to this side. So moment divided by weight would equal arm. When we want to calculate the airplane's CG, we're going to add up all the weights and all the moments and then all the weights, and then we divide those numbers to get the CG. So weight times arm equals moment. effects of high weight. So what are going to be the differences between when we are a lighter airplane, maybe solo with a minimum amount of fuel, versus fully loaded with passengers and fuel? There's going to be some differences. Most of them should be intuitive. Decreased performance. We have a heavier weight, a heavier mass to both support in the airplane when we're in the air, to accelerate and decelerate. So that heavier mass comes with some penalties. Takeoff distance will be increased because we have to accelerate that heavier force. Landing distance will be decreased. We have to decelerate that heavier force. A lower climb rate. So when we're climbing out, we're going to have a lower vertical speed per minute. We can see that on our performance calculation, so it'll take us longer to get to altitude. More stable and a higher VA. More stable, you could think about it and like this, is that if you have two airplanes, one is a 747 and the other is a Cessna 172, and a 10-knot wind gusts onto both airplanes, well, maybe the Cessna will get rocked just a little bit, but probably nothing would happen to a 747, okay? And so that's sort of an over-exaggeration of the idea of a heavier airplane has more inertia, it's harder to move than a lighter weight airplane. So that's why when we're heavy, we are slightly more stable. Effects of CG location. So then we have two images here. We have an aft CG, which is, this is the symbol for CG right there. So this red line represents the CG range. So there would be a forward CG range and then the aft CG. And so aft CG, just think about now, it is closer to the center of lift. And then we can see how much lift is required here. And we have our tail down force compared to a forward CG. So then now in a forward CG, we're at this edge of the envelope and it's acting down, and we have this further distance from the center of lift. I'm going to go back and forth, and I want you to just pay attention to when we have a forward or an aft CG, the amount of lift that needs to be created. So quite a bit when we have a forward CG. And an aft CG, well, we need to produce less lift to maintain straight and level flight. So we go forward CG, we're going to need some more lift. Aft CG, a little bit less lift. Okay, and this forward CG, we could see, and the reason why, I'll tell you quickly, is that this arm length, it's farther. So when the distance is farther, even though it's the same amount of weight, but it's positioned farther away, that arm length will have an increased effect or moment. And we need to compensate by creating more lift to counteract that. And so that is why the lift is more. So then now we're going to talk about the effects of an aft CG. We're going to have a lower stall speed. So when I'm talking about some of these, I could explain them to you, but then some of them we just want to commit to memory because these are going to be answers to questions. But we're going to have a lower stall speed. The reason why is because we saw the difference between those two images of a forward CG and an aft CG. On the forward CG, we had to have that more lift just to support ourselves in straight and level flight. But with the aft CG, we need slightly less lift to be produced. So then that equals a lower stall speed. Less stable. We're less stable because now we're closer to the center of lift. So the CG and center of gravity are closer instead of farther apart. The way I think about it is that if I'm standing with my feet close together and someone pushes on me, I'm a little less stable than when I'm down low and I got my feet spread wide apart. That is a more stable position. So that's how we can think about our forward and aft CG. An aft CG, our legs are close together, less stable. A forward CG, we're farther apart from the center of lift, and the CG, that's a more stable position. All right, but we're talking about aft. A higher cruise speed. Now this is for the same reason. When we have a aft CG, we need to produce less lift than with a forward CG just to maintain level flight. And then now, excuse me, a byproduct of that, of having to produce less lift just to maintain level flight, we would have, that equals a higher cruise speed. May not be able to recover from a stall or spin. This is mostly talking about if we were outside of our CG range and we made a mistake and we didn't load it within limits, and now we're out of limits to the aft CG. That leads to a situation where we might not be able to have enough authority with our elevator to overcome that and not recover. And the last one here, a short arm gives the elevator lower authority. So that's the reason why we might not be able to recover from a stall or spin, is that our elevator has less authority with a aft CG. Forward CG. So then here we saw this image already, but here's our CG range, and then now our CG is here forward, or a farther distance apart. Some of the effects of a forward CG, a higher stall speed. So we see compared to an aft CG, we have to produce more lift to overcome this forward CG. So that equals for us a higher stall speed. It's more stable. We talked about that with the feet position. When I have an aft CG, my feet are closer together. A forward CG, my feet are further apart. That's a more stable position. Lower cruise speed. So now with that CG forward, we need to produce more lift to overcome that forward CG and even level flight. Now that we have to produce more lift and level flight, that has the added effect of decreasing our cruise performance or our cruise speed. May not stall at all. Well, we're talking about reaching our critical angle of attack and rudder authority, or I'm sorry, elevator authority, and then so we may not stall at all. It's a pretty extreme case, but these are just individual items of a forward and aft CG. Poor climb, well, we understand that for those same reasons, with the forward CG, we have to produce more lift in just level flight, so then that has the secondary effect of affecting our climb. May not be able to flare at low power, determines forward CG. So I think we're talking about here aircraft certification and forward CG limits. How are they figuring that out? And then one of the things that we run into is that if you think about this, if we made a mistake and we have a very forward CG, we're out of limits, it's way out of limits, it's very heavy, and then now we're coming in for landing, we have this really nose heavy airplane, if you think about it in that fashion. Then what we need to do is we need to flare, we need to have elevator authority to lift that heavy nose up, that heavy forward CG. And then there's scenarios that we might not be able to have the elevator authority to overcome the forward CG effects. And that's what we're talking about there. Weight and balance calculations. So now that we have an idea of the effects of weight and balance, which is a very important when we're discussing it, and we understand what's going on with our airplane and the performance, now here we go, weight and balance calculations. So at the top part, step one, we want to print our weather and NOTAMs and verify our required documents are available. So in the pre-flight routine that I teach, print weather and NOTAMs is the second item. So we need to print those first because we're going to use those while we are performing this weight and balance. So we have our weather and NOTAMs. That's just part of printing our weather and NOTAMs. And then now we're going to verify our documents are available. Photo ID, license, medical, weight and balance, well, we have that right there, and then a flight plan if we're going on cross countries. So I put those boxes there. It's important to have those items with us, right? So it's just a reminder. So we assemble those items. We have everything that we need. Now it's time to start putting it in. Here we have our pilot's name. That's my name. Due back time. What time are we scheduled to come back? And then our aircraft tail number. Don't worry about here the takeoff and landing CG. We haven't actually got to that part yet, but we'll get to it. All right, step number 2, we're going to input our data and perform calculations. Remember, weight times arm equals moment. So then now we go through these items right here. The arm lengths, those are fixed distances that we've that I extracted from the POH in order to make this document. But what we're going to do is we're going to go find the basic empty weight for the airplane, and we're going to find that in the POH that's inside your actual airplane, and each plane's a little bit different. I'm sure you know this, but we need to find out what's the actual weight. Most FBOs will have a list for you that says what the basic empty weight is, so you don't have to go out to the airplane to get it, but that's where the basic empty weight goes. Then we're going to add in our front pilot and should be front passenger. So the combined weight of you and your flight instructor. Aft passenger, well, there's no aft passengers in the Diamond 20. Baggage, well, we have a max baggage of 44 pounds. We actually have 10 pounds. There is no baggage 2 compartment in the Diamond 20. And then we add that up, and we're going to, and then let me back up. So then we have our pilot and front passengers. So we got this weight. If we times weight times arm equals this moment. So that's what we do. We just bust out our calculator, multiply those two numbers together, and then we get the moment. And then we do that with each weight that we add. Okay, so then here we get to our zero fuel weight. Depending on the planes, the bigger planes you get in, there is a max zero fuel weight that you need to be careful of. I don't think it's a big concern in the smaller airplanes, but anyway, you might have a limit. So the max zero fuel weight for your airplane, make sure that you're not above it. Okay, now fuel. We have 24 gallons is the maximum, and then it's going to, just a reminder, 6 pounds per gallon. So we have 144 pounds. Remember to put the weight and not gallons in here. So we have 144 pounds. So whatever that was, it might be full. 6 times 24, I think that is 144. So we take that 144, times it by 32 to get that moment right there. Now we can calculate our ramp weight. So we have a ramp weight, that's how much the airplane weighs when we walk out to do our pre-flight. After we start it up, we have a fuel allowance for start, taxi, and run-up of 6 pounds. So we're going to burn 1 gallon by the time we complete our run-up and we're ready for takeoff. And then we get here, our takeoff weight. We have a maximum of 1764, and we are just inside it at 1717. And so this weight and balance is for a cross country that I talk about in the other video. But all right, so we have 1717, and then we added up our moments and then subtracted this startup and taxi one, and then we get our total here. So then we know moment divided by weight equals CG. So this is very important. All right, we continue on with our planning. We look at our nav log, and we determine that we are burning 42 pounds of fuel during the flight. We have the CG envelope for the fuel location, so we subtract that, and then now we're going to get our landing weight and landing moment. Okay? After we have those, which we see them over here on the right, we have our takeoff weight and takeoff moment. So we go up here, this is weight, and then this is moment. So then we just go up here, we have our weight, which is what, 1717. So I go over, and then our moment along the bottom, we go up, and then I make an X, and then I write beside it takeoff CG. We do the same thing for landing. We go over here, find the weight, 1617. And I understand that it's hard to read on this image, but when you're looking at it in real life, it's fine. We find the moment right there, we line those up. Some people, I usually all draw a line in between these two with an arrow. So I know when I take off to land, my CG is shifting forward. But the most important thing is that I understand that we're inside the limit. So we are good to go. And then just a reminder right there, this is the forward CG limit, the aft CG limit. This line here represents the max weight of the airplane, so we can't go above that. And then otherwise, we're inside the CG limits. So after we plot and verify that we're within limits, we'll move on to our next step, which is going to be calculate our performance data. So calculate and input takeoff performance. So I used that weather and NOTAMs to input my departure and arrival weather. And we're going to use that for our takeoff chart. So here I already know my takeoff weight from my weight and balance, so I input that here. Our field elevation is, I get that from our airport diagram. Will tell us what that field elevation is. So during the cross country, I plan to take off from this airport. It's 1,510 feet. Pressure altitude, 1,610. Now, I do go over the performance calculations in another video, but I can just remind you briefly. We see here the departure ATIS gave me a 2982 altimeter setting. So we remember that the altimeter settings go for tens, hundreds, thousands for those different points. So 2982 is 10, so 0.10 or 10. What is that? So that's lower than 2992 standard pressure. So if it's lower pressure than standard, then we think about lower pressure as being higher in the pool and then higher pressure being lower in the pool. That's the analogy that I give to students. Think about and visualize you're in a pool. You're in a pool of air. And we remember if we go deep into a pool, down in the deep end, we have that pressure on our ears. So that's a higher pressure. That would be a higher setting, like 3082 or something like that. That's a higher pressure. That would mean lower in the pool. But we're talking about 82. So that is lower pressure, which would be higher in the pool. So that's above. So then tens, hundreds, thousands. So that's 10, which would be 100, which means, and it's higher in the pool or higher altitude. So I take the 1500 and then I add 100, and then that gives me my pressure altitude. Okay, density altitude, here we have 2,900, and how we get that is from our temperature. So density altitude is going to be the difference between ISA and the current temperature times by 120 will give us the density altitude that we need to either add or subtract. Typically it's add to our pressure altitude. So ISA for our airport, and we have to remember ISA is 15 degrees Celsius. The elevation here is 1,500 feet or 1,500 feet above. So if it's 15 degrees Celsius at 0, then if we go up 2 degrees and we lose 2 degrees per 1,000 feet, then if we go up to 1,500 feet above sea level, then that's going to be 3 degrees less for ISA, our starting temperature. So we get 3 degrees less, we get 12. 12 degrees C is going to be our ISA temperature. And then we need to see what's the difference between 12 and 23 is that 11? And we take that number, and then now we have the difference between ISA and our actual, multiply that by 120, and then we'll add that number to our pressure altitude. And then here, in this case, we got 2,900. And I know that's a little bit confusing. There's a couple of different ways you can do it. You could use a calculator of some sort, right? Like just a thing on the internet you find, or just watch the performance calculations presentation that I have, and then we get to learn that. So sorry for hanging us up on there. Regardless, we're filling in this information, and then we have our headwind and crosswind component. We use the chart for that as well. Now we could go over to our weight and balance chart. This is on the back, our takeoff performance chart on the back. And then this dashed line represents all this information over here. So we go with our temperature. So we find our temperature down here, which this is degrees C. We go up to our pressure altitude that we had calculated, which was 1610. We go over, now we need to go down to our aircraft weight, which up here is our aircraft weight in pounds. And so aircraft takeoff weight is 1717. So we go down to that. We go over, and then here we have our headwind or tailwind component. So it looks like we went down for a headwind component. We go over, And then here is if we have an obstacle. And then we go up for the obstacle, come over, and then here's meters and feet. So then now we take that number, and then here we have a takeoff distance required of 1,900 feet. We look at our airport diagram, it tells us we have 8,200 feet of takeoff distance available. We're good to go. So I know it took me quite a while to get through and explain the density altitude calculation, but regardless, we're going to pop through, enter in all this information. This is very important. We get our takeoff distance and our takeoff distance available, and where we could run into problems is an extremely high density altitude airport. Think Grand Canyon Airport in the summertime. Grand Canyon Airport is already at 6,000 feet, I believe. Then you add in density altitude, it could be up to 10,000 feet. Now if we try to use 10,000 feet over here, we're going to get a lot different number. We come all the way up to here, I mean, we're getting a significantly different number, and pilots have run into problems. So that's why I'm taking the time to explain that now. Okay, so regardless, we got our takeoff data. Now we want to calculate and input our landing performance. So we look at our landing weight that we calculated. We input that here. We go over to our landing distance chart. We find our height, our distance, and then we input our distance here. And this is actually going to be a different chart. So the landing distance available is 6,800 versus that 8,000. So we go to a different airport in this lesson, but we look and we see, all right, what's my distance that I'm going to need based off my landing weight, and then how much distance do I have available? That checks. It's good to go. Now we're going to revisit those questions. So how are you going to know how many people you can carry and where they should sit? Definitely going to be a popular question that you could expect to be asked during your check ride. So how many people can you carry? Well, that depends. If we could either carry a certain amount of people or a certain amount of fuel. So if we want to take 4 passengers in a small airplane, we're probably not going to be able to take full fuel. And the reason why is we're going to run into the max weight of the airplane. Then we talk about where should they sit. If you have a big, huge bodybuilder guy, will just be nice, okay? Big bodybuilder type guy. Like me, I weigh over 230 pounds. So if you have 2 of me, you'd rather have the 2 heavy people sitting in the front, and then your girlfriends or the lighter people sitting in the back. And the reason why is because of the weight and balance considerations. And then you'll just be able to perform that, and you can do the calculations with the heavy people sitting in the front and sitting in the back as an example, and then you'll be able to see that it's likely you could go outside of your Aft CG range if the heavier people are sitting in the back versus sitting in the front. So arranging, how you arrange your passengers would be an answer to this question, talking about where they should sit. What's the maximum fuel you can carry while remaining in limits? Well, that depends on how many people we have. So if it's just you on a solo cross country, probably going to be able to get full fuel in that plane. But depending on how much your instructor weighs, then you might not be able to carry full fuel in your plane. So what's the maximum amount of fuel? Well, that depends on the weight of the people. Now we could take some of the people out and say, hey, we'll come back and get you, or I'm sorry, we can only take 3 people today and not 4 because we need this amount of fuel, that sort of thing. And what are your options? Well, I was just discussing those. We could take less people or less fuel, add in a fuel stop on our way. Those are all options for you. Hey, that's it for this lesson on weight and balance. Thanks for your attention, and I'll see you on the next video. Hey, hope you received value from watching this video. If you'd like to learn more from me, I invite you to take advantage of a free 14-day trial of FltLabs mastery programs. And inside, you're going to learn how to take control of your training, elevate your flying skill, and experience a new level of confidence in the cockpit. So, link for that's in the description below. Check it out, and I'll see you on the next video. See ya!